Welcome to another episode of Explained by AI. Have you ever wondered, what light actually is?
Yeah.
I mean, we see it every single day, but it's pretty wild when you really start to think about it.
Yeah.
Light can bend, it can split into, all the colors of the rainbow.
Yeah.
And it can even act like tiny little bullets of energy.
Yeah.
So get ready to have your mind blown, because today we're taking a deep dive into the amazing world of light and how it's connected to heat.
You're absolutely right. Light is way more complex than it seems at first, and understanding it can unlock a whole world of fascinating phenomena.
Oh, yeah.
From rainbows to lasers to the way we see the world around us.
Okay, so let's start with something we all see pretty much every day.
Okay.
A simple glass of water. Have you ever noticed how a straw looks bent or even broken when you put it in a glass of water?
It's a classic optical illusion.
It is.
And it all boils down to the way light travels through different materials. You see, light actually changes speed when it goes from one material to another, like from air to water.
Wait, so light slows down when it goes into water. Does that mean it speeds back up when it comes back out into the air?
Exactly. Light travels fastest in a vacuum, which is basically empty space. And then when it enters a denser material like water or glass, it slows down.
Huh.
And that change in speed is what makes the light bend.
That's so cool. So that's why the straw looks broken. The light from the part of the straw that's underwater bends as it's traveling from the water into the air, making it look like it's in a different position.
That's right. And to really understand how this bending happens, we can imagine an invisible line called the normal.
The normal.
Yeah, which is perpendicular to the surface where the light enters that new material. So when light travels from air to water, which is denser, it bends towards the normal.
Okay.
And when it goes from water back into the air, it bends away from the normal.
So it's all about the angle. But why does light bend at all when it changes speed? What's, the science behind that?
So it's all about how light interacts with the atoms and molecules in these different materials. When light enters a denser material, it interacts more with those particles, which slows it down and causes it to change direction.
Okay, I think I'm starting to get it. So light bends when it goes from air to water. But what about when it goes through something like a prism? I know those can make rainbows, but how does that work?
That's where the concept of dispersion comes in. So white light, like the light from the sun, is actually a mixture of all the colors of the rainbow,
Oh, wow.
each with a different wavelength.
Wait a minute. You're telling me that white light isn't its own color, but a combination of all the colors. That's mind-blowing.
It is pretty amazing. And just like waves in the ocean can be long or short, light waves have different wavelengths too.
Okay.
So red light has the longest wavelength and violet light has the shortest.
Huh.
Now, when white light passes through a prism, something really cool happens.
I bet it splits into a rainbow.
You got it. That's because the different wavelengths of light bend at slightly different angles when they pass through the prism.
Okay.
So violet light has the shortest wavelength, so it bends the most. Red light with the longest wavelength bends the least.
Oh.
All the other colors fall in between, creating that beautiful spectrum we call a rainbow.
So a prism basically separates the different colors that are already hidden within white light. It's like a color decoder.
That's a great way to put it.
Wow.
And this principle of dispersion isn't just limited to prisms either.
Okay.
Have you ever seen a rainbow in the sky after a rainstorm?
Of course. Who hasn't?
Well, guess what? Each tiny raindrop acts like a mini prism, splitting that sunlight into all those beautiful colors.
Wow. So rainbows are basically just a bunch of tiny prisms working together. That's incredible.
Yeah.
But before we move on, I have to know, who figured all this out about light bending and splitting into colors? It seems like pretty complicated stuff.
Well, we have some brilliant scientists to thank for that. Back in the 17th century, two very smart guys named Isaac Newton and Christian Huygens were totally fascinated by light, and they both made some incredible discoveries.
I've definitely heard of Isaac Newton. Wasn't he the guy who figured out gravity because an apple fell on his head?
You got it. He was a brilliant physicist who did some groundbreaking experiments with light.
Oh, okay.
And his most famous one involved a prism. He proved that white light is made up of all the colors of the rainbow by shining a beam of white light through a prism and then watching it split into that spectrum of colors.
So he basically created a rainbow in his lab. That's so cool. But what about that other scientist you mentioned, Huygens? What did he discover?
Well, Newton believed that light was made up of tiny particles called corpuscles.
Okay.
But Huygens had a different idea. He thought that light traveled as waves.
Waves.
Kind of like waves in water.
Hold on. So they had totally different theories about what light actually was.
Exactly. And it's really fascinating because both of their theories actually helped us understand how light bends and splits into colors,
Huh.
even though they had different ideas about what light itself is made of.
Wait a minute. So is light a wave or a particle? Can't be both, can it? That's like saying a car is both a truck and a motorcycle.
That's where things get really mind-blowing. Prepare yourself for this. Light can actually act as both a wave and a particle.
What? Seriously, how is that even possible? That's like some kind of superpower.
It is pretty wild, but it's a fundamental concept in physics known as the wave-particle duality of light. It basically means that light can behave like a wave sometimes and like a particle at other times.
Okay.
Let me try to explain it with an analogy. Imagine a pond with ripples spreading out from a dropped pebble.
Okay.
Those ripples are like waves of light, but light can also act like tiny packets of energy,
Okay.
kind of like little bundles of light, and we call these packets photons.
So sometimes light acts like a wave spreading out.
Right.
And sometimes it acts like a particle, like a tiny bullet of light.
Yeah.
But how do we know when it's doing which? Does it just decide randomly?
Well, it's not random. It depends on how we are observing it.
Okay.
When light bends or spreads out, like when it goes through a prism or creates ripples in a pond,
Okay.
it's acting like a wave. But when it interacts with matter, like when it hits a solar panel and knocks electrons loose, it's acting like a particle. It's almost like light has two different personalities,
Yeah.
and it chooses which one to show depending on the situation.
That is so bizarre. It's like light has a secret life.
It does.
And speaking of secrets, we've been talking about light carrying energy, but what about heat?
Yeah.
How does that fit into all of this?
That's a great question, and you're right to connect those two. It turns out that heat is actually another form of energy that travels as electromagnetic radiation, just like light.
Really?
Yeah, we can't see it with our eyes, but we can feel it as warmth.
Wait, so light and heat are both kinds of electromagnetic radiation.
Mm-hmm.
But if they're both the same kind of thing, why can we see light but not heat?
It all comes down to wavelengths again.
Oh, okay.
The radiation we feel as heat, called infrared radiation, has longer wavelengths than visible light. Remember how we talked about how red light has the longest wavelength and violet has the shortest in the visible spectrum?
Mm-hmm.
Well, infrared radiation has even longer wavelengths than red light,
Wow.
which is why we can't see it with our eyes.
So it's like there's a whole invisible world of light out there that we just can't see because our eyes aren't equipped to detect those wavelengths. That's amazing.
You're exactly right. And here's another fascinating fact. The hotter an object is, the shorter the wavelengths of radiation it emits.
Okay.
That's why the sun, which is incredibly hot, emits both visible light, which we can see, and infrared radiation, which we feel is heat.
So the sun is like a giant light bulb, blasting out both visible light and invisible heat.
Exactly.
But what about things that aren't as hot as the sun, like us?
Yeah.
Do we emit radiation too?
Believe it or not, even our own bodies, which are much cooler than the sun,
Yeah.
emit infrared radiation.
Right.
That's why we can feel the warmth of another person standing nearby, even if we can't see their heat.
Wow, so we're basically like little walking radiators giving off heat all the time.
We are indeed.
Now I'm imagining myself glowing in the dark with infrared light.
Well, it's not quite visible to our eyes, but it's definitely there.
That's so cool.
And speaking of heat, let's talk about something we all love on a chilly night, a campfire.
Okay.
We can see the light from the flames and feel the heat radiating from it. What's actually going on there?
Yeah.
How is that fire creating both light and heat?
Yeah, it's so cozy.
It is. Let's break down the science behind a campfire.
Okay.
When you burn wood, you're essentially releasing energy in the form of heat and light. This process is called combustion, and it involves a chemical reaction between the wood and oxygen in the air. Think of it this way. The wood contains stored energy in its chemical bonds, and when you burn it, those bonds break apart, releasing that energy as heat and light.
So it's like the wood is letting go of all its energy in a fiery explosion of light and heat.
Yeah.
But how does that actually work? What's happening at like the atomic level to make that light and heat?
On a more scientific level, the electrons in the wood get all excited and jump around when you add heat.
Oh, okay.
When they settle back down, they release that extra energy as light. And this light includes both the visible colors we see, A and D, the invisible infrared radiation we feel as heat.
So the campfire is basically like a mini sun, sending out both light and heat, all thanks to excited electrons.
Exactly.
That's pretty awesome. But what about other invisible forms of light, like radio waves? If we can't see infrared light, how do radio waves work, and why can't we see or feel them?
That's a great question. Just like light and infrared radiation, radio waves are a type of electromagnetic radiation, but they have much, much longer wavelengths than visible light. We're talking wavelengths that can be anywhere from millimeters to hundreds of meters long.
Whoa, that's huge compared to the tiny wavelengths of visible light.
Hmm.
But why can't we see or feel radio waves if they're all around us?
Yeah.
I mean, they're used for so many things like radio and TV, and so they must be pretty powerful, right?
They are powerful in a way, but not in the same way as visible light or infrared radiation.
Okay.
It comes down to our biology and the energy levels of radio waves.
Yeah.
Our eyes are only designed to detect a very narrow range of wavelengths, which is the visible light spectrum. Radio waves fall outside of that range, so we simply can't see them.
Okay.
And because radio waves have much lower energy than infrared radiation, we don't feel them as heat either.
So even though we can't see or feel them, radio waves are still zipping around us all the time.
They are.
They sound like little invisible travelers, carrying information and entertainment.
That's a great way to put it.
This deep dive into the world of light and heat has been mind-blowing. We've learned so much about how light bends, how it splits into colors, the dual nature of light as both a wave and a particle, the connection between light and heat, and even the invisible world of radio waves.
It is truly fascinating. It's amazing to think that all of these invisible waves and particles are constantly interacting with us and the world around us, shaping our experiences in ways we often don't even realize.
It's like there's a whole secret universe of light and energy that we're only just beginning to understand. But before we get too lost in the mysteries of the universe, maybe we should take a step back and recap some of the key things we've learned today.
That's a great idea. Let's revisit those amazing facts about light.
Okay, so first off, we learned that light is a lot more complex than it seems.
Mm-hmm.
It can act as both a wave and a particle, which is pretty mind-blowing.
Right. That's that wild concept of wave-particle duality. Sometimes light behaves like ripples in a pond spreading out and interfering with each other.
Yeah.
But other times it acts like tiny packets of energy called photons, transferring energy when they interact with matter. It all depends on how we observe it.
And we also learned that light bends when it travels from one material to another because it changes speed.
Right.
That bending is called refraction,
Mm-hmm.
and is what makes that straw look broken in a glass of water.
Yes, and the amount of bending depends on the angle at which the light hits the surface and the difference in density between the two materials. Remember that invisible line we talked about, the normal?
Uh-huh.
Light bends toward the normal when entering a denser medium and away from the normal when entering a less dense medium.
It's all about angles and density.
No.
And then there's dispersion, which is how light splits into its different colors,
Mm.
creating those dazzling rainbows.
Right. White light is actually a mixture of all the colors of the rainbow, each with a different wavelength. When light passes through a prism, those different wavelengths bend at slightly different angles, spreading out the colors and creating that beautiful spectrum. It's like a color decoder for sunlight.
So a rainbow is basically sunlight being dispersed by raindrops acting as tiny prisms.
Exactly. It's amazing how such simple things like water droplets can create such stunning displays of light and color.
We also learned about two incredible scientists, Isaac Newton and Christian Huygens, who helped us unravel the mysteries of light. Newton, with his famous prism experiment, showed that white light is made up of different colors,
Yeah.
and he thought light was made of particles.
And Huygens, on the other hand, believed that light traveled as waves. Both of their theories were groundbreaking and helped us understand light in new ways, even though they had different ideas about its fundamental nature.
And in a way, they were both right. Light can act as both a wave and a particle, depending on how we observe it.
Yes, it's a concept that scientists continue to explore and debate even today. The wave-particle duality of light is one of the most fascinating and fundamental concepts in physics.
And speaking of fascinating, we also talked about how light and heat are connected.
They're both forms of electromagnetic radiation, but with different wavelengths. Heat, or infrared radiation, has longer wavelengths than visible light. And the hotter an object is, the shorter the wavelengths of radiation it emits. That explains why the sun emits both visible light, which we can see, and infrared radiation, which we feel as heat.
Even our own bodies emit infrared radiation, which is why we can feel the warmth of another person standing nearby. We are all little walking radiators, constantly radiating heat into the world.
We are indeed. And a campfire is a great example of how heat and light are produced together through the process of combustion.
When we burn wood, we release the stored energy in its chemical bonds as heat and light, with those excited electrons jumping around and releasing energy as they settle back down. It's like a mini sun right in front of us.
Exactly. And last but not least, we explored the invisible world of radio waves, which are also a form of electromagnetic radiation, but with much, much longer wavelengths than visible light.
Even though we can't see or feel them, radio waves are all around us, carrying information and entertainment over long distances. They're the invisible messengers of our modern world.
It's truly amazing how much we rely on this invisible form of light for communication, from radio and television broadcasts to cell phones and Wi-Fi.
It's like we're living in a sea of invisible waves connecting us all. This whole deep dive has been incredible. We've gone from basic concepts like refraction and dispersion to mind-boggling ideas like the dual nature of light and the vast invisible world of electromagnetic radiation. It's amazing how much we can learn from simply asking questions and exploring the world around us.
Absolutely. And who knows what other mysteries of light and energy are waiting to be discovered.
That's what makes science so exciting. There's always more to learn, always more to explore, and always more mysteries to unravel. And the best part is, anyone can be a part of the scientific adventure.
Yeah, it really is amazing what we can learn about the world just by being curious.
And that's what we're all about here on Explained by AI, right?
Yeah, absolutely. Curiosity is the key to unlocking all sorts of amazing knowledge.
Exactly. It's like having a superpower that lets you see the world in a whole new way.
It is. When you start asking questions and looking deeper, you realize there's so much more to discover than meets the eye.
It's like we've been talking about today with light. We see it every day, but when you really start digging into the science behind it, it's just mind-blowing.
Right. From bending and splitting into colors to acting as both a wave and a particle, light is full of surprises.
And it's not just light. The whole universe is full of these incredible phenomena just waiting to be explored.
And the coolest thing is that anyone can be a part of that exploration. You don't need to be a scientist or have a fancy lab to make amazing discoveries.
All you need is that spark of curiosity and a willingness to ask questions.
Exactly. So keep exploring, keep asking questions, and keep that sense of wonder alive.
Well said. That's all the time we have for today's deep dive into the world of light and heat. We hope you enjoyed the journey and learned something new along the way.
It's been a pleasure sharing these fascinating insights with you.
If you have any topics you would like to have explained, drop them in the comments.